Hello everyone, this is Himanshu Kumar Paul, a PhD candidate majoring in operations research from University at Buffalo. I welcome you all to the presentation on the article titled Fast Active Sampling for Top K Rank Aggregation from pairwise Comparisons by Maximizing the Expected Value of Experimentation. I am presenting on behalf of the authors, that is me and Dr. Alexander Nicolai, an associate professor and the director of graduate studies of the Department of Industrial and Systems Engineering, University at Buffalo. I would like to begin with the theme of the work. In many applications, the top K commonly most preferred items can be identified by procuring annotators pairwise preferences of the items. However, soliciting pairwise preference information for rank aggregation can be costly, particularly when human annotators are involved. In this work, we present an active sampling algorithm that at any stage of this rank inference problem selects the most informative next pairwise comparison to solicit based on maximizing the expected value of experimentation. The algorithm's logic and efficiency are demonstrated on both synthetic and real-world datasets. Let me ask you a question. Who are the top 10 chess players of all time according to you? Probably not an easy question to answer. Chess.com has made a list for you. Maybe an easier and more intuitive question is whom do you prefer between Garry Kasparov and Magnus Carlsen? Pairwise comparison informs us about the preference order between a pair of entities. In many applications, people can provide better judgment towards a pairwise comparison rather than in a list-wise or point-wise comparison. Pairwise comparison is a popular method of data collection often used in voting systems, scientific study of preferences, social choice, etc. Other applications of pairwise comparisons include multi-criteria decision making, supply chain and logistics management, recommender system, multimedia information retrieval, etc. If multiple human evaluators are involved with pairwise comparisons, then the comparison results often become noisy or inconsistent. Since different evaluators will have different order of preference about the same set of items. Although a single evaluator's order of preference should be consistent, the aggregate information of all evaluators' partial order of preferences become noisy. Rank aggregation techniques are developed to learn a consensus ranking from few pairwise comparisons. However, there are two major challenges associated with rank aggregation techniques. First, most rank aggregation techniques assumes a passive approach to learning. Pairwise comparisons or partial rankings are collected in a random or non-adaptive fashion and then aggregated to obtain a full ranking. As a result, huge number of pairwise comparisons are required to learn the full ranking. Second, soliciting pairwise comparisons can be expensive and time-consuming. In applications such as scientific studies and market research, pairwise preferences are collected from human evaluators over a set of items for scientific understanding or product placement. The scope of these experiments is often very limited simply due to the time and expense required to collect the data. A possible solution to these problems is active sampling technique that selectively collect pairwise comparison data for rank aggregation. As a result, fewer comparison results will be required to obtain a consensus ranking. In this work, we address the problem of selecting the best k out of n items with high probability on the basis of a finite number of noisy pairwise comparisons. In this process, we would like to propose an active sampling algorithm that strategically and iteratively select most informative pairwise comparison based on available comparison results. Before we delve into our model, first I would like to discuss two renowned models of this field. Bradley-Terry model is one of the most commonly applied models for the analysis of paired comparison data. It's a probability model to predict the outcome of a paired comparison. The model postulates the existence of a latent preference vector. According to this model, probability of winning of an item over another depends on their preference scores. This model has a wide array of applications. Real-world applications of the model include measurement of auditory attributes, assessment of risk associated with aircraft wiring, analysis of citation patterns of scholarly articles, etc. Rank centrality is a random walk-based rank aggregation algorithm, which can be utilized to learn the true value of the preference vector under Bradley-Terry model with high probability. Rank centrality falls under the category of spectral ranking algorithms that utilize the leading eigenvector of a transition probability matrix representing the comparison's outcome to find the global rankings of items. The algorithm has a natural random walk interpretation over the graph of items with an edge present between a pair of items if they are compared. The ranking score of an item turns out to be its stationary probability under this random walk. The algorithm generates a transition probability matrix from noisy pairwise comparison to represent the random walk. Under ideal setting with infinite samples per comparison, rank centrality model generates a transition probability matrix out of the pairwise comparison results, which define a reversible Markov chain under the Bradley-Terry model. That is the stationary distribution approaches towards the true preference score according to Bradley-Terry model. Now I will try to explain how decision theory can be applicable for an active sampling study. Let's take a toy example with 5 items, where the items can be evaluated by noisy pairwise comparisons. A decision is to be made about the top 2 items based on the available pairwise comparison results. Let's assume a state of nature S is an unordered list of potential top 2 items out of these 5 items. The set of states of nature comprises of all possible true top lists constructed out of 5 items. The cardinality of this set will be 5 choose 2 or 10. A state of nature is represented as a binary vector of length 5, where the value corresponding to an item will be 1 if it makes to the top list and 0 otherwise. When no comparison results are available, the prior probability of all the states of nature will be same, which is 1 over 10. A decision alternative is a choice of top 2 lists from the set of possible true top lists. A reward function can be designed to evaluate a decision based on the state of nature. The reward function tells us how many top items a decision correctly identifies from the true top list. For example, the reward will be 2 if a decision correctly identifies top 2 items of the true top list. If no further information is available, the optimal decision D star will identify the true top list as per the current belief. The expected reward from the optimal decision will depend on the reward function and the prior distribution. Now assume new pairwise comparison result can be solicited at a certain expense. We consider a pairwise comparison as an experiment. If we can solicit a new pairwise comparison, then the updated optimal expected reward will depend on the reward function and the posterior distribution. The belief about the prior distribution of two top lists can be updated iteratively using Bayesian update process. According to the Bayes rule, posterior probability can be calculated if prior distribution and conditional probability measure on experimentation for every state of nature are known. We can randomly select the first pairwise comparison to initiate the process. For this example, let's assume a pairwise comparison between item 1 and 2 is to be performed with one possible outcome is item 1 wins over 2 and another one is item 2 wins over 1. Now the conditional probability of a certain outcome for a given true top list can be defined as follows. Both the items will have equal probability of winning if either both the items belong to the top list or neither of them makes the top list. If only item 1 makes to the top list, then it will have a high probability Q of winning. On the other hand, if only item 2 makes to the top list, then item 1 will have a low probability 1 minus Q of winning. Since we don't know in advance what outcome will be obtained, we need to consider all possible outcomes to calculate the updated expected reward for a given comparison. The expected reward will depend on both the posterior distribution of true top list and the marginal probability of a certain outcome of an experiment. Now the task of selecting the best pairwise comparison for next iteration that maximizes the expected reward becomes equivalent to the expected value of experimentation maximization problem. As the selected pairwise comparison is performed and the result is obtained, we can then decide about the top list based on the updated prior distribution. The issue with this approach is the set of possible top lists can be quite large. For perspective, if you would like to identify top 10 items out of 50 items, the possible number of top lists will be over 10 billion and the number of possible experiments will be over 1200. As the number of items increase, the Bayesian update process and corresponding expected value of experimentation calculation becomes computationally intractable. In order to efficiently estimate the posterior distribution after a comparison result is solicited, we incorporate rank centrality algorithm in our model. We consider the probability of a state of nature as a function of the ranking scores of top items for that state of nature. If we have t comparison results available, then as an example of this state of nature with item 1 and 2 as the top items, the probability that this state of nature is the true top list will be equivalent to the summation of current ranking scores of item 1 and 2. Then the optimal expected reward becomes equivalent to the summation of ranking scores of top two items based on t comparison results. Similarly, the posterior probability after a comparison result is solicited will be equivalent to the summation of ranking scores of item 1 and 2 based on t plus 1 comparison results. The estimated EVE will depend on the change in ranking score after an iteration and the marginal probability of an outcome of a comparison. However, this is still not a computationally efficient method. For perspective, if we would like to identify top k items out of 50 items, this method will need to recompute the ranking scores of all items 2450 times for a single iteration. It is a very challenging task to make an algorithm computationally faster without losing accuracy. However, we find a smart way to efficiently calculate the expected value experimentation without sacrificing inference accuracy. To make the computation more efficient, we turn towards the highly mathematical work of Golub and Meyer to understand how the ranking scores are obtained in the first place. They utilize the concept of group inversion and keyword factorization to identify the direction and magnitude of change in stationary probabilities of Markov chain over a change in transition probability matrix without recomputing the stationary distribution again. Based on this concept, we further investigate and identify that a pairwise comparison result changes only a small portion of the transition probability matrix, a mere 2 by 2 submatrix portion only. This small submatrix corresponding with only two rows of the group inverse matrix. Hence, we reformulate Golub and Meyer's equation to only consider the portion of the matrices that contributes to the change in stationary distribution, and we obtain a much more efficient approach to compute the expected value experimentation. Our algorithm mainly contributes to the scenario where a large number of possible experiments exist. The algorithm calculates expected value experimentation n times faster than the original version. Here we present the first active sampling algorithm. The algorithm takes the transition probability matrix and stationary probabilities of Markov chain, calculates the group inverse matrix and expected value of experimentation for all experiments, and returns the most informative pairwise comparison for next iteration. Now I would like to demonstrate our model's effectiveness on both synthetic and real-world datasets. We select three synthetic datasets with number of items 10, 50, and 100. First, we identify top 1 and top 3 items for the 10 item dataset, and then top 1, 5, and 20 items for the 50 and 100 item datasets. The comparison results for the synthetic datasets are generated according to predatory model using predefined true preference scores. We also showcase the robustness of the proposed method on a real-world dataset NASCAR. The NASCAR dataset shows ranking of drivers from NASCAR 2002 season racing results. The NASCAR dataset has 87 different drivers who competed in a total of 36 races, in which 43 drivers were racing at each race. The true ranking score is estimated using rank centrality algorithm on the entire dataset. Our algorithm's performance is compared on few randomly selected data with new comparison results solicited from complete dataset. We compare performance against two baseline models, random sampling method that randomly selects sample pair for comparison from the set of possible candidates in case of synthetic data or available candidates in case of real-world data. Rule-based sampling method selects the current best ranked item and the least compared item for comparison. We consider mean absolute error as a performance metric. That means we calculate the absolute difference between the ground truth ranking score and the inferred ranking score for each iteration. Let's take a look at the error plots. The x-axis represents number of iterations and y-axis represents the mean absolute error. The blue curve shows the performance of our algorithm. The lower the value of MAE, the better. First plot shows performance for identifying top 1 item, and the second plot is for identifying top 3 items. Here we can see that our algorithm performs way better than the baseline. The algorithm performs slightly poor here when an inconsistent comparison result is solicited in the initial iterations. However, this issue can be resolved if we consider multiple random replications and take average error over all replications. This is the performance comparison on real-world dataset. In conclusion, our work explores the possibility of using decision theory to efficiently obtain next pair of sample for rank aggregation from noisy pairwise preferences. In turn, we propose a fast active sampling algorithm by utilizing the simple and intuitive concept of EVE. In future, we would like to benchmark performance of our algorithm against other published works. We want to incorporate the confidence interval of ranking scores to obtain probability distribution of two states of nature for better prediction performance. Also, we would like to identify the dominant pairwise comparisons based on the expected value of experimentation, which will allow us to exclude a large portion of the inferior comparisons from calculation and in turn will make the model even faster. I will stop here. Thank you all for your patience.